plane. So we're going to be dealing with complex numbers. There's going to be a lot of stuff like definition-wise that you may not need to write. I would probably not write this part. Actually, I might not write this whole thing. Just because it's going over different ways to graph. So we've graphed rectangular, that's your normal X and Y. We did polar, which is our crazy circle graphs. And now we're going to start adding in complex numbers. So we got our lovely little review of this is a complex number. I would draw that in your notes. And remember, A plus BI means this part is A, and this part up here is B. Oh. I would just be like graphing complex numbers. Boom. This is how you do it. And I did get a date for COSI. May 22nd. It's a Monday. It's after exams. I made sure it was after AP exams. It's pretty doggone for sure. It's $10 for you guys to get in. Seemed manageable. And if not, come talk to me. But they did offer to go into the King Tut part, but that's an additional $13. I don't know if I want to pay an extra $13 to go see an old dead dude. All right. Ready? So our next one with the example is we're just going to plot or graph this complex number. You got to tell yourself you're not a fish. Hey, 6th period did it, and it actually worked. You got to say it, I'm not a fish. Hiccups are going to be gone. And I know that because I was really upset about it. All right, so if I'm graphing root 3 minus I, it's going to be down here in my 4th quadrant. And square root of 3 is somewhere between 1 and 2, right? Yes, no, somewhere around there. Now, that minus I part is really saying minus 1I. So let's say this is square root of 3, and then this is negative 1. My point Z would be right here. So far, so good. Easy enough. All right, so we got some definitions. All right, we're going to talk magnitude. Magnitude is essentially the Pythagorean theorem. It is your distance. I noticed you're not hiccuping anymore. No worries. All right, so what do you guys notice about magnitude? Is it similar to anything we've done before? What? Polar coordinates? Basically Pythagorean theorem? You can if you want to, or you could just say it's Pythagorean theorem. All right, ready to scroll? So magnitude, when they write it, it actually looks like absolute value signs. So it's not saying find the absolute value of z, it's saying find the magnitude. I would probably put that as a note somewhere, because this is the notation for it. I would definitely have this part, but that's just me. All right, ready? So conjugates, we have already kind of talked about, but I do want to point something out real quick. So notice the little bar. I don't know why it's floating way up there. It should be a little closer to the z, but whatever. So we end up calling this z bar because we're super creative. All right, but basically we're just saying if z equals x plus yi, then the conjugate, z bar, is x minus yi. You can write the show that part and make sure you leave space. So do you want to do this in terms of x's and y's, or do you want to pick numbers for it? X and y? Yes, no? We want to go x's and y's? Okay. So I tend to just start with left side and right side. So magnitude of z equals, and we're just going to say z equals x plus yi. All right, well, when finding the magnitude, it's just the square root of x squared plus y squared. Yes? Now I got to deal with the other part. This piece is saying z times its conjugate. So what would be z bar for this problem? Z bar is x minus yi. Can I multiply those two together? It's going to be alphabet soup, but it's manageable. So I've got x squared, xyi, minus xyi, minus y squared, and I squared. Now what do we remember about I squared? Yeah, it's a -1. So this all becomes just a positive y squared. Now notice it's under a square root, correct? And these two drop off. So square root of z times z bar equals the square root of x squared plus y squared. Are those the same? Bueno. Easy enough? Yeah. Ready to scroll? Okay. So, how does all this crap relate to polars? Remember, x equals r cosine of theta and y equals r sine of theta. So, big important pieces, I would say, like, complex number to polar is going to be literally just this. So I would write all of this from here down. anybody go to Disney in here, did I? Scroll so you can see a little bit more. All right, notice down here at the bottom, theta we tend to keep between 0 and 2 pi, not including 2 pi. Also notice, because it's math and we've got to call everything 12 different names, they start calling theta the argument. I don't know why argument fits with theta, but whatever. All right. And then we've got these two examples. We ready to do examples? I did want to point out, you guys see this? So this was a shorthand that my students had ended up writing. God, how many years ago is that now? 9 years ago. It's basically the abbreviation of CIS in here, because they just wanted to be lazy with it. So, I always give it as an opportunity, like that's an option, although my math lab probably will not accept it. Okay? Now we got two examples. Do we want to start easy and then go to more difficult? Okay. So take a second, write it down, and then we're going to start with the right side. All right, so starting with this right-hand side. What's the cosine of 30? What is it? Yeah, I don't know either. Yeah, square root of 3 over 2. So square root of 3 over 2 plus I times, what's the sine at 30? Yep, 1/2. Now I've got a 2 on the outside. If I distribute that in, what happens to my fractions? Yeah, they all cancel out. So it is square root of 3 plus I. All right, ready to go opposite direction? So this is kind of the buzzkill with it, is there's more work to go from complex into polar than it is to go vice versa. So the first thing I got to do is I got to find the magnitude. So root 3 minus 1. What is square root of 3 squared? 3 plus 1 is 4, yeah. Square root of 4 is 2. Cool. Halfway done. Now, if we want to be a little lazy, we could look at the problem we just did. What's the difference between the one on the right versus the one on the left? Yeah, it's a flip into the fourth quadrant. So, we could either mathematically go through and solve for theta, which would be tangent inverse, which just gives you 30 degrees. But technically it should be a negative 30 degrees. Yes? Now, was negative 30 within our restrictions for theta? No. So it's 360 minus 30. Yeah, 330. So, radius, cosine, I, sine of 330 degrees. 2 cosine of 330 plus, and they might let you do it with parentheses, which does make your life a little easier. You'd have to expand it all the way out. All right. Keep going so we can have a work day? Okay. So, day 2, which, let's be honest, we're just continuing. And they want us to remember that we've got these different functions. But we literally just talked about them. So, do we want to write them down or no? You may also want your purple sheet. All right. On the back of the purple sheet, I think I've got most of these formulas for you guys. Do I have Democritus? I do. Go me. All right, so right down here under the complex number part on the back, these are your formulas. Okay, so one of the big things is what happens when you need to multiply and what happens when you need to divide. All right, so when you multiply complex numbers, it is radius 1 times radius 2, parentheses, and then you just add your thetas. So if you want to write that in on your notes, I would literally just write this box. All right, same thing with division. I'm going to do 8. Can I scroll a little bit? All right, so the last part is De Moivre's theorem. I don't care if you say his name right. I assume it's pronounced De Moivre. Oh, it's French. I'm going with the French pronunciation. So this is just basically how do I work with raising a complex number to an exponent? So what are we thinking about the formulas? Terrible looking, not so terrible? Are we falling back asleep? Almost not, I promise. All right. So, yes, we found these on the back of the purple sheet, which is nice, because they're all there. All right, so first one we're going to do is raising it to a power. And I'm moving your MyMathLab back for this week. Make it due on Friday. We have our Unit 10 test, and then we've got a Unit 11 test, like Chapter 11, and then the final exam. We're done. No more quizzes. Well, because and if you guys look at the calendar, I put in there which days we have late start, so you guys know. But yeah, all that state testing crap's coming up, so we've got a lot of 30-minute classes. All right, ready? So, which one of the formulas am I using? Yeah, the Dude's theorem, De Moivre. All right, so remember, when you're doing this, take your radius, raise it to that power. And then inside, I've got cosine of 3 times 20 plus I sine 3 times 20. What's 2 cubed? 8. And then if you want to abbreviate, it's literally it. Oh, crap, yeah. Yeah, you're right. So 8, let me rewrite it all out. Cosine of 60. All right, so what's the cosine at 60? 1/2 plus I root 3 over 2. All of this times 8. So my fractions disappear. So I'm left with 4 plus 4 root 3 I. Now it's A plus BI. How we feel? We okay? Mer? All right. Here's our next one. And I would personally try to get this in cosine I sine format. So do you guys want to try that on your own? No. I got a couple people just, no, don't leave me on my own. I'm just going to fall back asleep. 1, 1. I wrote way too close. So you've got 1, and then you've got I up here. So I've got to find my radius. So square root of 1 plus 1, square root of 2. And then theta, any ideas on the theta? Are my legs technically equal? Yeah, pi over 4, or 45. So pi over 4, or 45 degrees. It's basically a 45, 45, 90 triangle, but with complex numbers. Yeah. Is that better? Yeah. But you're plugging in the leading coefficient for the I. You don't plug in the I. Yeah. So all of this breaks down to square root of 2 cosine 45 plus I sine of 45 to the 5th power. Now I have to go through and actually use that theorem again. So here's the thing with the square root. I can't do anything nice with that. So you could leave it as square root of 2 to the 5th power if you really want to. You could put it in parentheses. You could write it as 2 and then 5/2. It's kind of whatever floats your boat. But do we remember that these are equivalent? Yeah, Jack? What did I say? Or square root of 2. Yes, technically you could. So Jack went and did this. 3, 4, 5. So this is 2. This is another 2. So that is 4 root 2. Want to do it that way? No, just leave it the way we had it. Well, so right now, I'm just doing the radius part of it. So remember on De Moivre's theorem, this thingy? So when you do it, it's r to whatever that exponent is. And then we just multiply our thetas by that exponent. Okay, so we were just messing with the radius first. All right, so whatever floats your boat with the radius, I'm going to leave it like this. Now I've got cosine, and then it's 5 times 45. So 2 makes 90, another 2 makes 180, plus a 45, 225. Yeah, did I math that right? Okay. Yeah. So, Caitlin, for the step I skipped, I literally just did 45 times 5, and that's going to equal my theta to the 5th power. The next one. Yeah, it's hideous. All right, ready to find the complex roots? This is ugly. All right, so I would definitely do this. All right, n as a square root needs to be greater than 2, and then k is going to be each of our different roots. All right. I don't think I actually put this one on the purple sheet. Is it? Yay, smart me. Yep, theta naught. Yep. Yeah, theta naught. Yeah. It's ugly. Yeah, it's the same. It's just, Caitlin, what, on mine, I didn't split these into 2 separate fractions. So on mine, I kept it as theta plus 2k pi all over n. I just left it like one fraction. Because it seems excessive to split it all the way out. All right. And you definitely do want to have this bottom part because that's going to tell you how many roots you need to find. All right? And how many k's you need to bring into it. I feel like our poor little brains are regretting saying, yeah, we'll do double notes on Monday. You're like, shouldn't have done this. All right. Ready? As ready as we're going to be? Okay. This is our last problem. All right. So, find the complex roots, cube roots. That's important. Yep. So, cube roots. So, third root, yeah, that's going to be n. And then leave your answers in polar form with the argument in degrees. All right, so before we panic, I've got to get the complex number in the polar form first. Yes? So, do you want me to write out steps? Okay. Step 1. Rewrite -1 plus square root of 3 times I in polar form. It shouldn't be, but it somehow managed to get under there. Alright, so when you go to rewrite it, I tend to draw a little picture. So I've got a -1 here, and then I'm going up square root of 3. Yeah, the CIS. So step 1, I've got to find the magnitude. So what's square root of 3 squared? 3. And then what's -1 squared? So this just equals 2. Last part is I got to find the theta value. Now, if you want to use your calculator and go that way, you can. Mike? 2 pi over 3? I was going to say, or 2 pi over 3, but notice it says write it in degree mode. Yep, 120. Yeah. So remember we did the 1 plus root 3i, or root 3 plus 1i earlier, and that gave us the 30 down here. This is literally just a 30, 60, 90. Alright, so all of this works out to being 2 cosine of 120 plus I sine of 120. Still step 1, yep. Alright, ready for step 2? As ready as we're going to be? We're almost done at least. So, when they said cube roots, how many roots is that? 3. So, cube roots means n equals 3. So, step 2, find the roots. And remember, they had that bottom thing with k on the formula. So k is going to be 0, 1, and 2. That part? Do we want to write that part in? Okay, write that part in. Theta naught's just your initial theta value. Okay? Because I gotta make them sound smarter than they are. So you always go k, 0, 1, 2, 3, all the way up to n minus 1. Yep, that's why we're stopping at 2. Alright, now the radii on this are all the same. Alright, so I'm going to go through and I'm going to do k equals 0 first, and then we're going to do k equals 1 and k equals 2. So your first step on this is cube root of your radius, which is 2. Leave it alone. Now the inside part is going to be cosine of, if you look at your formula sheet, it's your original theta value. So 120 plus 2 pi k divided by n. 2 pi and then k. K is 0, yep. plus I sine of all that same crap. Except what is 2 pi times 0? 0. So really it's just 120 divided by 3, which is 40 degrees. So cube root of 2 cosine of 40 plus I sine of 40. So there's my first one. All right, which one do I need to do next? 1. So we'll go green. K equals 1. So does my radius change? Nope. So it's cube root of 2 cosine 120 plus, now notice they write it as 2 pi k and that's in radians. What's another way of writing that? Yeah, 360 times 1. Still over 3. So what's 120 plus 360? Divided by 3? 160. So cube root of 2, bless you, cosine, what did you say it was? 160? Do we want to try k equals 2 on our own? Kyla's like, don't leave me. Alright, I'll pass back quizzes while you guys try. So it's opposite over adjacent. What's 840 divided by 3? 280? You were like, I was getting there. All right.